maybe a year almost. Like we started with the Math Olympiad effort at Google, and has been continuing since then on other aspects. So this work is mostly focused on the work we've been doing on the inference time work stream that we have at Google for reasoning models and reasoning capabilities. We have also a lot of work going on training, and I can't say too much about that, but there's I think very good opportunity for research as well, and so I wanted to maybe share a little bit of what I can say share with you guys. All right, cool. So good. So what's the state of the art right now in reasoning models for math, for frontier research with AI, right? And so the main question here is in the past, a lot of the work has been done towards being easy benchmark, or what I call easy benchmark. Of course, 2 years ago they were not easy, but now they're easy. But they are very specific benchmark where you have very clear verifiable answers. And these very clear verifiable answers are of the form of you have a math question, now we give you 4 answers, pick the right one. And so then we can very easily verify that the model picked the right one. And from there, people have evolved towards slightly more advanced, where you have a math question and the goal is to derive the right formula or derive the right number out of this math question. And again, it's not so hard to verify that, right? It's not maybe exactly pattern matching, but it's very close to pattern matching, right? But of course, if you start going after Math Olympiad, for example, which is the baby version of frontier math research, then the challenge here is that it's still verifiable, but it's what we started calling soft verifiable, in the sense of you give me a proof, now I have to verify that proof. And if we ask everyone in this room whether this Math Olympiad proof is correct, probably we'll get 100% accuracy, agreement. But if we start asking whether this stock paper, the proof of that stock paper is the correct proof, some people may it's not very clear that we'll get that much accuracy. You can see it in the reviews, you can see in all this. You will have disagreement of exactly, even within the human community, we'll have disagreement of what's actually a right proof or not, right? And so you start to have to face these things, and you start even facing it, to some extent at the Olympiad level. And at the Olympiad level, we can all agree the proof is correct, but there is a grading scheme, and this grading scheme is very specific. And if I'm asked to grade a Math Olympiad proof, I will probably not agree with the official graders who have been very much instructed on how they should grade this, right? So now we have to deal with this verifiable proof that have an objective underlying ground truth, but they are not as verifiable as multiple choice question or hard-coded 42 answers. Okay, and so that's what we want to do, is to go after this. And it's also asking a new, I think, core problem for the current models, which is, I think, the more philosophical problem on the current models, which, and I don't know exactly what the answer is, and that's what it's research is usually when you ask a model right now, it will try to give you an answer. And if you ask it once, even the current models, they will run once, explore mostly 1 or 2 ideas, and then give you an answer. And this answer could be a correct answer, could be an incorrect answer, could be I don't know, no matter but they will not have this diversity, they will not provide this diversity of solution that we go after when we are tasked to solve a hard math question, right? So if we go after a hard math question, you will explore different paths, remember some of it, discard the bad ideas, combine them, etc. And it seems that with one single query to an LLM, this is not what's happening. Okay, so this core problem here, one can ask: is it a missing capability of the model? We want something to teach the model to be able to do. And if yes, then how do we do it? And the other thing is okay, well, to fix that issue right now, what we should be doing is what's called inference scaling, and probably have some sort of agentic pipeline where the model is we're gonna make multiple calls to the model to try to patch this issue, right? And of course, like, it's not clear whether the answer is going to lie both in the patching and in the training, or in the training only eventually, right? Like, we don't know that yet. Okay, cool. So the result that we got last year was that this interesting milestone that now Gemini is able to get like a gold medal at the Math Olympiad, and then it was able to solve like 5 out of 6 problems. And we can see that now the current models are able to actually go to 6 out of 6 models. And so we see the pace is actually pretty fast, right? Like, a year ago, January or February last year, probably the model were able to solve like, 2 or 3 out of the 6 problems. And these days they are able to do the whole 6 problem without that much more, compute than what was there. And so there's a very good increasing pace here, like, for being able to do research. And this definitely asks the question of like, okay, well, how do we go from this level of research to frontier, right? Like, because this is still IMO, we all love IMO, but this is for high school students, right? So we want to go beyond that. Okay, good. And maybe the thing that is interesting to note here is that 2 years ago, it was possible to achieve like a silver medal at IMO based on a system that was not a Gemini, LLM model, that was, some sort of LLM model combined with like lean, and so formal verification. And at the time, this seemed to be the right path. But like 1 year ago, what we showed was that actually you can do everything with text, and you will be able to still get the total score of points. And the lean pass is not needed. Like, a formal verification is not necessarily what's the important ingredient when we go after those things. Feel free to interrupt if you have any question or yeah.
Yeah, so was lean not used at all in the 2025?
Yeah, that's right. Yes. And I think maybe the right mental picture for this is that the same way that we don't write papers with lean right now, the model don't write paper, like they don't attack the math piece of question with lean. Good. Following up on that, there was like another effort that we also put, which was also trying to go after this ICPC. So I don't know if everyone is familiar with that, but it's like, algorithmic programming, like, type of, it's the IOI, but for, so the informatics Olympiad, but like at a slightly higher level, because this is for college level. And it's also possible to go after that, which is also an interesting thing, where it's a mix of like reasoning for the algorithmic side, but also like execution in terms of code, right? And like, managing to write the actual code that implements the algorithms, the right algorithm. And yeah, again, there was like interesting things. It's like, on the same amount of time, the model was able to solve some problems that the humans in the room did not manage to solve in the same amount of time. So it's interesting. Hopefully we can push that further. And all of this effort is to try to go beyond, the current human capabilities. Okay, so let's try to step back a little bit from these insights and like, the state of the art, and try to make it like slightly more, yeah, sorry.
Characterize the problems that it was.
Yes. Okay. So actually, one of them that is particularly hard is some sort of computational geometry problem. And maybe the interesting thing is that this computational geometry problem, it's, you would often in computational geometry, we assume things are in general position. And a lot of the aspects of solving that problem was that things were not in general position. And there was a lot of corner cases for that problem. And the model was not so able to identify these corner cases and be exhaustive against that, right? Because the way these contexts work is that you have these hidden test sets where you have to be fast enough. The algorithm has to solve the test case fast enough. They have all of these test cases have like different kind of like corner cases, etc. And so the model, like the solution, has to be correct on all of them. And the model was not correct, I think, on these specific computational geometry problems that had a lot of these corner cases that we can imagine for computational geometry. Good. So, okay, so let's try to do a little bit of science out of this. Like, yeah, it's a fast-moving pace, so we try to do a little bit of science, but it's not so easy to do science. So the goal of this talk is to also try to propose like some kind of like framework for thinking about these problems, and you know, we propose the framework, but this framework is not like the golden standard framework. We should just like, you know, start from this framework and you know, iterate over it. So you know, usually what's happening when you query this model once is clearly this behavior that is a little bit bogus in the current model, which is the model will make a genuine attempt at solving the problem and make like, you know, tiny mistakes. So you will have missing one step in the reasoning. You will have you know, logical like or calculation error that is like a tiny thing, not so important, but like still there, or like some hallucinations, right? That are there. And one single generation often has this issue. And so it's very tempting to fix it in training, but like it's not so clear how you fix this type of thing in training only. And another way to attack this problem is to try to generate more solutions and try to do some filtering or try to combine this solution into a correct one, right? And so this is what the inference scaling type of techniques are after. And really the guiding question here is like, how do we find for the correct or, you know, make this, have this incorrect solution percolate into a correct one, right? So there are different ways of modeling that, and I think that's an exciting direction. Okay, so the first thing you can do is have this decomposition of like a generation step where you try to generate a bunch of solutions and to explore the set of potential ideas that could be helpful to solve a given problem. So, you know, you can ask the model to generate various solutions, and you can do it in a way that you increase the diversity, right? So really, like, you know, what you want is that the model tries all possible ideas that are reasonable for solving this problem to generate a bunch of like directions, right? Which is a little bit what you do in research as well. But when you're asked to solve a given problem, you know, well, maybe I should try this idea, or this idea, or this idea. So maybe the idea is that, okay, first you generate like a bunch of solutions, and you have this pool of ideas, mostly incorrect or flawed, or like, you know, barely promising, but like not completely true. And the second step would be, okay, well, now we have all of these ideas. Can we ask the model to, you know, combine them, make them percolate into one final solution that would be the right one, right? Like combine these ideas. So it's really a filtering process in some sense. But like, you know, also modification, combination is also important here. So you can take these solutions that you generated, feed them back into context, and ask the model, okay, well, now generate a new solution for this problem, but, you know, use these previous insights that you had to generate a new one. Okay. Okay. And the question is like, okay, can you improve the simple generation, the one solution generation that we discussed in the previous slide with this kind of two-stage process, right? And the question here, I think this is an interesting question here because you are not necessarily injecting new information into the system, right? It's like the model creates the information. Like the model creates information, and it's, you know, if this process works, then it finally solves the problem better than if it had only one generation, right? And so there is an intrinsic behavior or an intrinsic capability that is, you know, underlying in the model, like latent in the model, right? That is, this model is capable of solving that problem because based on all the information it generated, it got the right answer. But, you know, if you ask it once, it's not able to, right? So how do you make this latent capability the bigger governing capability of that model such that it's a better model, right? So I think that's the, you know, fundamental question that we are asking here. And if you want to look at a more forward-looking question, the question is like, is this type of issue an intrinsic issue of the current model architecture or the current models in general, right? Or is this something that is like, you know, no matter how good the models will be, do I need to kind of like, will there always be some latent capability hidden in the model that I would have to extract from the current models? Or is there hope that, like, you know, we can reach a model that is, you know, I code it once, I observe the result, and that's the best capability of the model, right? And I think it's a very interesting question, but, you know, we don't know the answer yet. And good, yeah.
How do you check for correctness? that stage, the first stage gave you incorrect things, why is stage 2 miraculously correct?
So okay, so mostly what I'm so mostly for Math Olympiad, there's a lot of human verification of like graders that would do
So
that.
it's a human guided rather than like.
Oh, sorry. Yeah. Sorry. So okay, there are two aspects, right? So one is like if you want the metrics that we report or the metrics that the results of the Math Olympiad, they were all human graded. So all of this is like based on the human, but it's not a human search. It's like we submit one solution to the model, to the human, and the human says right or wrong, right, or give some scores, right. Now the two-stage process, this should be fully automated. That's why I'm saying there is no external information added to the process. It's like we generate this set of solutions and we feed them back to the same model, and now the model reasons about this information that it created. Does that answer the question or? Okay, Jose, can you rephrase the question?
Well, one of the purposes of Lean was to have formal things that you know for certain that it's correct.
Yeah.
Here, it seems like purely in the LLM.
Right.
There's no check mark that says, oh, this is absolutely correct.
That's right.
Process.
Yes.
So it's interesting that in the first step, you get this ideas like reasoning and generation, and then the combination of that is use the same model or something different, but it somehow has an increased chance of being correct.
That's right.
Just by nature.
Yeah, I mean, but like by nature,
I mean,
in the same way that we would.
More likely because of the Google suggestion.
Yeah, exactly. Yes, the idea. Yeah. I think that's a very, but it's also very close to. I mean, it's also very close to the way we do research, right? As in, like we can come up with ideas, and the first version of the idea is wrong. The next iteration is correct, right? Like, and I think that's exactly what's happening in these models. And we have a lot of examples where you can ask the model to tackle a given question, X many times, and you get X many wrong answers. Then you give these X many wrong answers to the model, and it derives the correct one out of it. So it's because the models are also good at self-predicting, like at predicting math as well. Which is actually a good introduction to the. So does that answer the question? Like, yeah, okay. So which also give like the next slides, which is okay. So this is a little old, but like it's like this Gemini Flash model. So it's a small model, so not as strong as like the biggest model we have. On this Amy 25 dataset, which is a math dataset, which is like fully verifiable, so very like much easier than Proofs. And you can sample like we have this interesting experiment which is like, okay, what's the number of correct solutions that we observe on 100 samples? Okay, so we sample like for question 7 we sample the model 100 times, we get 100 answers, and then we see that about like 70% or like 75% of them are correct. Okay, so this is what we see here, right? So we can see that like for some of these questions, they are very easy. Some of them are there, but like, maybe the interesting questions are the one for which the model, like, from time to time gets it right on one, maybe 8 or 8 or 11, but like it gets it right at a level that is not very satisfactory, especially if you're competing at IMO. You don't want to, make sure that you will succeed only with 20% probability you get your gold medal, and otherwise you'll fail. So it performed well at a level that is not so good, right? And so the interesting empirical experiment we can make out of this is that now let's focus on this, like 1, 8, and 11. So there's a little delay. Okay, yeah, 1, 8, and 11. And let's try to make the following experiment, which is we take this, we take like some number of wrong solution and add them into the context, and we can see the number of the capability of the model at generating a good solution out of these solutions, right? So okay, so the experiment here is like we give one correct solution and X many incorrect one. So X ranging from 0 to 8, and we ask the model now, derive your own solution. So, not surprisingly, if you give a correct solution and 0 other wrong answer, you are, not really, the model is pretty good. But if you start injecting wrong solutions, you see the model gets confused. But the interesting phenomenon here is that it gets confused. It's still be able to be above this red line, which is the baseline, right? This is a generation probability, right? And so maybe the interesting thing is here is that for questions where this generation probability is pretty high, or like even I think all of these questions are actually pretty close to this. The probability that within 4 or 3 or 5 answers, right, you get a correct one is actually high, right? Like it's not so bad. It's not so these are about 20%. So the probability that over 5 answers you generate a correct one is reasonable, and then the probability that you can filter it down is actually also reasonable. So this is a empirical study that shows that you can generate a bunch and then ask the model to filter down, and then your probability of success is actually higher. You're boosting it's a boosting phenomenon, right? Like you're saying, okay, well, I have this bunch of things, and now I try to boost. Okay, yeah.
What happens if you do not include the correct answer?
Right. So if you do not include the correct answer, then you will get something that is slightly above, the baseline. The baseline as you increase the number of answers. So it does have this phenomenon of I have this bunch of ideas, and sometimes they do percolate into a correct one. But I don't have the plots because this is with a flash model, and I think this phenomenon is more apparent with a bigger model. The flash model is a little bit dumb, so I was already happy that it's able to do the filtering correctly. But I think the new flash models and the bigger models are much more able to do this filtering better and combination better.
I think the other thing is even if you have the correct answer, it could be a really long with each hand thought, right? So did you guys see what happens in that scenario?
Oh, so right now we just give the answer, we don't give the thoughts.
Oh.
Right? Like we just take the thoughts of the generated thoughts, that's the input to the next call. The generated answers, that's what the input to the next call. The thoughts are all dropped. We just, yeah.
What's the
So this red line is this probability. It's it's this number here. I think it's a green line. The green number here, the green number there, and the green number there. It's like the probability if you sample once. So this is basically showing by making more calls, you do get an improvement over the baseline. Which is this phenomenon that is kind of interesting, and I think modeling modeling this phenomenon is an interesting thing that I think we don't understand very well, and it's something that may be useful to understand whether this type of inference scaling techniques are needed, or it's possible to kind of teach the model to do it itself. Okay, so the two-stage model, seems to be performing reasonably well. Which this two-stage again is this generation plus filtering. That's an interesting thing, and the model is indeed able to combine and filter, right? So that's also the interesting thing is that if the model is given a wrong proof, it's not so bad at saying it's a wrong proof. I mean, it's not perfect, right? It's a bit false positive and so on, but it's able to actually identify reasonably well what's the correct and incorrect answer. Okay, so here, if you want to milk the capability out of the most reasoning capability out of these models, it seems that you need these refine and combine, generate, refine, combine type of loops. Okay, and so I can't say too much about what's happening internally, but I decided to mention 2 works that have been happening publicly. So I went to go these 2 works, and actually this first work appeared at the time of the Math Olympiad. So this is another group, but at Stanford, I think, who was working on some sort of inference scaling pipeline on top of Gemini as well for trying to solve the Math Olympiad problems. They created the following pipeline, which is generate. So you have a solver agent that goes and try to make a genuine attempt at the problem. And then you have the reviewer / verifier here, which will be presented with this proof, make a critique, try to classify the errors between like, critical errors, mistake, like tiny mistakes that need like more justification and, things that are good. And then there's out of this, reviewer reports, like, feedback, we provide this feedback back all the way to the verifier, to the generator, and ask the generator to fix that issue. Okay, so you keep on having this loop of generation, verification, and generation again. Okay, and the work that they did was like to repeat this until the verifier succeeds, like until the verifier approves for 5 consecutive times that the answer is valid. I think because like if you have a failure, then there will be a bug report that is fed, and so the generation will generate a new proof. So you will not be verifying the same thing.
The bug report says there are no bugs. Is it still required? Is the proof that it's still required to generate a new proof?
Yeah, it's still saying like, okay, well, can you no, it doesn't generate anymore. Like we just ask the verifier one more time. So you keep on verifying the same thing until you find a bug report or you succeed 5 times. And the idea is that there is randomness, like the process is stochastic, right? Like you have like randomness in the process, so the verifier will not output always the same thing, right? It will keep on. So sorry, this is the pipeline. So you have the initial solution generation, try to self-improve a little bit, then verification. If you have a bug report, you have a correction step done by the verification. You go back, you verify again, and then if you succeed, you. And at the end, like if you keep on failing, at some point you just stop, you give up. That's the thing, right? So okay, so you keep on making new model calls through this pipeline. But the interesting thing out of this is that they managed to show that there is a big bump in accuracy here. And so here the idea, so these numbers have to be taken with a grain of salt because they are human verified, the number are human verified, but they are not done by the experts, the graders. So again, as I said, like even though I can understand the math Olympiad proofs, and I can say whether they're wrong or bug, like they're bug or not, the scoring is like over like 7 points, so from 0 to 7, and whether you get 4 or 5 is a very delicate discussion, right? So these numbers they are done by themselves, which I'm sure they are great at, but I don't think they have like IMO grading experience, so we have to be a little bit careful. But the boost is so high that I think it's an interesting phenomenon that we see here, that plugging this pipeline on top of the Gemini 2.5 Pro or GPT-5 or Grok 4, you will go from some accuracy here to some much higher accuracy. And I think that really here is you manage to extract this latent capability I was mentioning here that brings you to a capacity, like a capability of like 85.7% accuracy on this model, on these things, that is like latent in these models. But now by having this pipeline, which is like a fully automated pipeline with no external information, you are able to hill climb pretty drastically the baselines. Yes.
Is it pass up search you pass that search you, or you ask the model to choose?
No, it's really good. This is the best of 32. So I think you ask the model to pick ones. So you generate like 32 answers and ask the model which of these 32 answers is the right one, and then that's the final solution.
I'm wondering what's the right pass answer.
I think good. I think pass 32 is not going to be more than 50% on these things. And again, I think for the same reason that the first generation is not formal and detailed enough to be a valid, what we would consider as valid proof. It would be a sloppy proof. So maybe the pass 32 is like 100% on like sloppy, no, not 100, like maybe 85% on sloppy proofs. But if you want an actual proof, you need to kind of have this verification.
Can you give us some idea of like the overhead in terms of compute you need? So like progressive 32 presumably is create a model 32 times plus a verifier or something. for the, something like the VR pipeline, how much more compute is needed, how many like moves do we all involve?
Is if I understand, okay, so if my memory is right here, it's about the same ballpark for these numbers. In what they show, and that's why they show the 32. I think is because on average, that's the kind of numbers they will get. If I mean, don't quote me on that. I would need to double check, but I think this is the idea is that if I give you a budget of 32 calls, you can either do or 33, then you can either do 32 calls and ask for the best, or you can try to do a more advanced pipeline of self-verification, and then you can really climb much better. Good. So now there is this other work that I think is kind of an interesting work, and I should check them not. So I have another like 15 minutes or something, or
Yeah,
yeah.
15.
Yeah, okay. Okay, good. So good. So let me talk about this other work that is slightly more recent than the IMO work, which is coming from the Mila lab at in Canada, which is it has very much like the same flavor, but it has a new ingredient that I think is also very interesting, which is that so you view this as a genetic algorithm. So how do you view this as a genetic algorithm? Well, let's generate a population of n solutions. All right. So if you have this, let's say you generate like 16 solution with high temperature. So all of these solutions are like different 16 ideas, and then you keep on iterating and refining this solution. So you basically make this genetic algorithm over solutions, over mathematical ideas, and to generate the next population of ideas, what you want to do is that you will subsample a set of like few solutions, like k solution at random among your population of n, give them to the model, to the current model, and ask the current model to generate a new solution based on these k ideas, right? And you repeat that n times, and that gives you a new population of n ideas, right? And you keep on iterating like this until you, after t steps, like as many compute budget you have, you get the final population of solution that is there, and maybe you make one final call to pick the best one, whichever scoring function you have to make this. So it's essentially a genetic algorithm where you're scoring, or like metric for selection, like your selection metric here is basically a call to the LLM to analyze k solution and generate a new one. Okay, so it's a very cute idea, very natural idea. And it's kind of combining the previous ideas with this. It includes the previous idea, which is that you want to keep you really have these two dimensions. One is like the horizontal here, like each line here is a set of ideas, and the columns here are like iterations over these ideas. So you do this verification, this self-verification of all these ideas and critique, right? So you keep on critiquing these ideas, and hopefully, as you critique them, you improve them. But here there is another angle that is also interesting, is that you keep a population of diverse ideas, right? You have to keep a population of approaches to tackle a problem, right? And for Math Olympiad, the interesting thing is that a lot of the Math Olympiads, they are about techniques, right? So, you need to have this proof technique, which is math, which is like some induction, and then the other proof technique, which is like, this specific lemma that we teach you in high school that you need to use cleverly, and so a lot of this Math Olympiad problems are a clever combination of this type of techniques, and by doing this type of methods here, you indeed have a pool of diverse techniques. And if you put them all in the context at the same time, you hope that the model is able to combine them cleverly. I think that's the power underlying here. Yeah.
There seems to be a trend between these ideas where you started with very independent solutions, and now you're like each idea you're telling us about is kind of increasing the interplay between those solutions.
Yeah.
So I wonder if you consider the framework where you literally have different instances of LLMs working together.
Right. Yeah, I think that's totally valid. So rephrasing your question, I think it's whether you want these LLMs to be stateful or not, right? Like whether they have a memory of everything that has happened in the past, as you keep on iterating, right? And and I think this is a very interesting question. This is very fundamentally, like, I don't know whether it's good. I don't know whether it's good that the LLM keeps the context, or it's better to have an LLM that has a free context at some point. And because it seems that if you have a good context, then it's good to keep on iterating on it. But if you start having like misleading direction, then you keep diving into this rabbit hole that leads nowhere. And so it seemed to us, or at least in the experimental world, like it seems that having a stateless version of it, where you have a fresh agent each time, it seems to be more robust against this rabbit hole. But like I think it's a fundamental question of like how do we manage context in this type of iterations.
Yeah, you check how diverse they actually are.
No, exactly. Good. So I think this is actually I think it's also a very interesting question, which is like, okay, for Math Olympiad, you couldn't try to set up this notion of diversity by saying, oh, this is using method 1 and method 2 and method 5, and this one is like 3 and 4. And so you could try to classify them. But if we try to be looking forward to like, oh, I want to use this type of methods to do my own research, it's less clear how you would maintain this diversity. And in fact, I actually would like to enforce the diversity because, in many cases, I think they are not so diverse because, maybe there are not so many ideas. Like it's very unclear how many different ideas you can have. So it's very inefficient to have a prescribed number of different solutions because maybe for the problem at hand, you only need like 2 different ideas to explore. Maybe for this other problem, you need like 20. So it's very unclear. So it would be nice to have a more organic way of doing it baked into how we decode the solution, for example, of the model. And like, when we generate a new solution, we can see, when we generate this solution, there is only one solution out of this. So maybe that's enough. But like when I generate this new solution, there are actually 2 different branches that go here. And I would like to kind of like maybe keep these 2 solutions as candidate solutions. I don't know which branch. Sorry? Yeah.
Say, oh, these are far behind or something.
Yeah. The thing is, I don't really know how to train this autoencoder because it's, I need labels basically. Like it's an autoencoder, but I want to be able to say, oh, these 2 lemma, these 2 proofs, they are similar, but they're actually very different. They are talking about 2 different objects, but 2 mathematical objects. But it's just that the governing meta idea or the scaffold of the proof are similar. And so they would be similar, right? But like, so it's the similarity notion behind the encoder is not very clear. I mean, view it in a different way. It's a good research question. So there's a challenge here. Yeah.
So I think on small models, they've been trying to they're trying to make small models do like simple math, and they tried basically 2 approaches. Like one was like they looked at embeddings of different things, and then they reweighted based on the embeddings, like problem struggle. And the other one is they like asked an LLM, hey, extract out the skills that are used to like solve this like problem. It's like algebra, is it like geometry, and so on.
Yeah.
And they saw the skill thing that works. So
Yeah.
I want to try that. It's like
No, exactly. No, I think for the skills, I think the skill thing is what works and what worked for the Math Olympiad. So the skill, I think the embedding, I don't know, I think it's very far from, like it's a very deep research, I don't know how to make it work. But a skill-based classification, I think works well. I just feel like for research level, it's very hard to have a good skill classification. That's the challenge. But for Math Olympiad, already Math Olympiad, which is some kind of baby version of research, you can do the skill based classification.
Is you can look at the solution that they give the research questions, look at the solution that's written, and then look at every wrong step it makes, and then you can classify that with the skill.
Right. The thing that is tricky is that if I give you a problem, how do you generate the classification? Based on the problem statement,
You need to do it on positive. You need to like make the solution. You look at the solution and then.
Yeah, exactly. So if you don't have the solution, it's a tricky challenge.
No, I mean like positive.
Sorry.
So like, let's say you're trying to train a model.
Yeah. If you want to train, then you can try to do it. But like exactly.
I see. Got it. Thanks.
Okay, cool. So next. Okay, good. So more questions. So next thing is so good. So what they showed here was essentially that indeed, so what's the value of this method? So the value of this method is that you have basically two parameters, right? You have the number of steps that you will go, which is in this other pipeline was like the number of self-verification in some sense, right? So it's the number of steps of verification that you will go through and iterations, self-iterations. And you have the breadth, which is like the number of solutions that you are keeping in your pool, right? And I think these plots are interesting. So in the sense of like what they showed is that, okay, so the blue curve here, they are like, how many solutions? So you keep one solution. Okay, so you have one solution. So it's not really a generic algorithm. It's like one solution, and you keep on iterating over that solution until you for like 10 steps, right? Something like this. So you can see the blue curve, the quality is not super good. It's like it's there, right? It's like, and it's kind of the baseline, right? So you keep on iterating, and you can see that it goes up. So as you iterate, you indeed improve. That's interesting. But you can see that the other curve are also interesting. They also go up, and so as you iterate, you improve. But as you diversify, so as you have more candidate solution in your pool or in your population, and you keep on iterating over that population, you do even better, right? And so you can see a massive gap from getting one solution and iterating over it, which essentially tells you that you are going down a rabbit hole with like, one idea, as opposed to having a population of at least two, and two is orange. So there is already a big gap between blue and orange in many of these curves, where, except here, but like most of these curves have like this big gap between blue and orange because you have, with two ideas, you are able to not go down into a rabbit hole. Interesting phenomenon that you need these two dimensions, basically, the diversity and the iterations. Okay. Yeah.
This more or less answered it, but do you observe any like scaling laws here? Like these experiments seem to have like small numbers, so like if you really wanted to throw a lot of compute into this, do you observe that this is
yes, you do observe that, yes. I can't show the plots, but yes, you do observe this type of things. When you have a lot of compute and bigger models, you are able to diversify more, and then because the thing is that even if the idea appears one in like 150 example, or 1,000 ideas, the model is not so bad at picking up on the idea. So that's the thing that is reasonable. Good. So okay. So the maybe the summary of these two line of work, which I think is an interesting experimental setup we can discuss, which is like you have this sequential version of the pipeline, which is you keep on iterating, but you have an explicit verification step. So you have this explicit adversarial model that's going to go after you. So the proof, and with the weakness that you can go into this local minimum, this rabbit hole idea, and be stuck. And you have this other pipeline which is missing the explicit verification and critic. But it has this nice diversity of idea, which, as we show in the plot, is actually reasonable. Okay, so the idea, so the idea behind this works, and I think I don't have much time to go on theory work, but okay, basically, maybe the most interesting part is not the theory part that I'm going to go into afterwards, but it's more like, okay, here is a model of what we see in practice, and here are some experiments. Now, as theoreticians or people interested in doing science, what can we learn from this experiment? Bring a model, what can we model out of this and prove about these things, and also come up with new ideas on how to improve them, right? So I think that's an interesting part. Okay, so we have these theoretical results. We have a paper on arXiv about this stuff. I don't know. I don't need to go too much into that because I see that in time, but. So again, the idea was that, okay, we take these type of things, and now we're going to have these two parameters, n and k, where n is the number of candidates you have in the pool, and k is the number of things you can put in a query, and a query is a query to a model, right? So the query is like generate a new answer based on this k existing answers, and this k existing answer can be some of them can be correct, some of them can be incorrect, right? And of course, the query that you are making is going to be noisy, right? Like it's a query that may even if I have a correct answer and in my pool, the output of the query may be wrong because the model is not perfect, right? It can be full. Okay. So it's using so this is like very similar to a literature on the theory of computer science of finding the maximum of a given set of values with noisy queries, like noisy. So there is a noisy comparison queries where you say, oh, is this number higher or lower than that number? And it succeeds with some probability. And then you questions like, okay, can you sort? How many queries do you need to sort? How many queries do you need to find the max? So it's a very similar problem. So we have like some similar ideas here. So mostly the problem definition was that, okay, I give you a set of items. These are, let's say, generated solutions. And you can perform a, k array, like, take k elements in this set of n items, have the max, which is like, okay, give me the correct proof, give me a correct proof. And the goal is like, now we have these noisy queries and you can do it. So we have like some, essentially theoretical results. I don't need to go and we have some kind of query complexity results on this. I don't want to go too much into the detail. I don't have time anyway, so I'm going a little bit faster. But the interesting thing was that the number of queries you have really tells you how many solutions that you can compare. So it's really important in that setup to have a very diverse, like be able to bring together many solutions to generate a new one. And we have like it's like we have this type of results that says like oh, if you have like more the bigger the query, the more aggregation you can make, especially if you care about parallel, like if you try to count the number of parallel equations versus sequential equations. All right, I'm gonna conclude. Yeah, I don't have to go too much into that, but like yeah, exactly. So I have a bunch of like summary. So we have like this result at Math Olympiad, ICPC, etc. And the goal really now is the thing to go after like real state-of-the-art math results. And again, I think there is an interesting research question, which is like whether some of this lies into the training, and some of it lies in the inference time, right? Like how we can build like agentic pipelines that will help going after that. It seems that this diversity is very interesting, and it's a very powerful argument. And so we really need a way that the model, when it tackles a problem, it can, generate diverse ideas. And if you are going to query it once, you really want that your query is going to generate a bunch of diverse ideas, and the model is able to converge to the right one, right? And merge them in the right way. Okay, so again, like I think it's very open to have like good models for this type of things. I think there's a lot that can be done from the algorithmic point of view on understanding and modeling this type of pipelines and trying to optimize them algorithmically. And I think, again, also for training, how to train this pipeline to do better. So diversity and iterations and how we can teach the model to do it. Okay, so I think I'm at time. I'm a little over time, so I'm gonna stop here, take any question if you have more. Otherwise, feel free to shoot an email. Yeah.
I ask like, so you try these methods, for example, in like some often problems in science, how will this define that?
I think they have like if you really want to prove like a dilemma level, for example, like if you want to go and prove a lemma in yes, you do. I think you at this point, like even with the best models out there, you need this set of pipeline to do this type of thing, right? So it's still like state of the art. This type of pipelines are state of the art for making new discoveries. But I also think they are currently limited. They will not get you to proving like very advanced results, because the amount of it's like if you want to prove an advanced result, you probably don't. It's a long horizon task. It's like a task that goes over like a lot of tokens, etc. These pipelines, they don't handle the context management that well. So there are more ingredients that are needed in these pipelines to actually go after like very big theorem, right? If let's say you wanted to generate a stock paper or something like an important result, how many number of tokens you need to generate is like very much out of the context window of the current models. So you need more technologies than just this type of pipelines. But they do still improve the.
As you start to move from limited problems to more complex problems like research, the problem of verifying solutions becomes trickier.
Right.
For example, with all of these like first proof solutions
Right.
that have been coming out in the last couple of weeks,
Right.
it seems to be a very non-trivial task to even tell if the model is outputting a correct solution
Right.
or not. Do you have thoughts on how these, like, do you have plans of trying to integrate something about checking solutions into like what you're doing, like formally checking solutions? Is there any hope of
Right.
integrating this stuff into what you're doing here?
Yeah. So okay, good. So okay, so first off, I think the first proof work is really problematic in various ways, but like you have a simpler version which is like taking papers that have been published that after the cutoff. So they are still like fresh data. And for them you have a ground truth proof, which is not the case for first proof. The proofs are hidden. Now, if you have the ground truth proof, it's slightly easier to verify, even with natural languages. So that solves that makes a partial it's a partial fix to the issue you are raising. Ideally, going and having a lean verification of all of the generated proof, I think that's nice. Issue is that we it's like lean is too far behind in some sense, right?
Yeah.
But I also think it's maybe a red herring in the sense of like we don't need lean verification for writing the next stock paper or the next analog math paper.
But you trust the person writing the paper, right? LLMs routinely have.
No, but that's not how the analog math paper. It's not because it's.
But there is some credibility associated to the author who wrote. Like if the author repeatedly writes.
Oh, okay. So I think two things. No, I think okay. No, let me change that. What I want to do is I want to go after an important math result. I don't want to write just a stock paper or something. I want to go after a very important result. If it's a very important result, we can take the very important results that appear at Star Fox, etc. I don't know. We can talk about graph isomorphism. We can talk about all of this, right? So let's think about that level. That level, it's not because Laszlo Babai wrote this paper that we trust it. It's like it has gone through a lot of scrutiny. Actually, bugs have been found and fixed. So I'm happy to replicate that process. I don't need to press one button, get yes or no, and the proof and trust it blindly. I want to incorporate this type of system into a real, system that provides real science and interesting results. If we write just a new math result to claim, we have a new math result and no one really cares too much about, and indeed we need to rely on the author credibility to say it's correct, I'm not after that. We want something that is game changing, and so a lot of people will read it, and so a lot of people will be checking it, and then we can establish it like this, right? Like I'm more interested in that than exactly author credibility.
Right, but I guess I think a concern that's starting to come up is that as more and more resources begin to be devoted towards solving these problems, we might end up with LLM generating proofs that look like proofs and just contain extremely progressively more and more subtle bugs that become harder and harder to find. And it'd be nice if we could do something in the design step to try to discourage or prevent this.
Right. No, and I think it also goes. Okay, so I agree with that, but I'm also not sure the lead path is the right path.
I'm not.
Yeah. No, but like if you have, we were discussing that with with Mark before. Like if you have an eval of like wrong proof, and the goal is to make sure that the model is able to tell which one is wrong, which one is not wrong, and what are the bugs, etc. I think that's very valuable. If we can train the model to be better at detecting these bugs and improving them, then I think that's right. But I'm also not trying to make a system. I don't think we need to make a system that is cryptographically secure or something against my proof for having a positive impact on and getting interesting results on math. I think if we match the human capability, that's already interesting. But like, of course, the goal is to apply it in a clever way. We apply it towards an important problem. We just don't apply it to any problem in the world and overflow the whole thing. We really want to make it a good view.
Yeah, thanks for that. Speaking on context and specifically, so one results was really for I about one correct answer and incorrect answers. Is that robust to how you present the different answers to the whole?
Yeah, I think these days it's more or less, yeah. There was like this attention things and stuff like that in the past, but I think these days it's getting fixed. Yeah.
If they stopped funding this idea of like paying people to train it to translate English to Loon. So I saw a talk by Google last year at Institute for Advanced Study on alpha proof, but at that time they were still hopeful that they could
I think
English to Lean and even checking that's another thing. Yeah,
right.
It was correct at Lean, but does it say the same thing instead of English?
Right. No.
So like
definitely. No, I think we need that, and I think that's great, and we should push Lean as well. My view is that Lean is just it's one of the areas of math. It's like algebraic geometry. It's like one of these things, right? So there is a lot of work that needs to be done towards Lean. There's a lot of work to be done to make the model good at algebraic geometry, TCS, etc. All of these are parallel efforts. I don't think Lean is on the critical path of any of these things, right? Like in the sense of like you can get the new best TCS results or like something like this with the current natural language. It doesn't have to go through Lean. But of course, that doesn't mean we should stop Lean. I think the goal of the Lean community of like making all the generated math verifiable eventually, I think is a very legit goal, and we should push it as well. Like it's I think it's just separate efforts, like in this.
The population. Sorry, yeah, the population thing. How does the ideas evolve? Like, is it the case that like always in the first population you sort of have the version of the right idea and that's evolved?
So that's one part of it, but it also gets combined with other ideas. So you also have like more advanced proof, which combine different aspects of the, and also because often of this more complicated proof, you need to prove this first part, which requires some idea, and the second part, which requires this other idea. And maybe the first version was like a little bit sketchy on one and didn't have the second idea. And so now you get more and more fleshed out proof, basically.
Maybe we can thank Vincent again and a big